Okay, I hesitate to say what I'm about to say because sometimes if I say it, if I say what I'm going to say, some of you might go, oh, and throw your hands up and bail. But I'm not saying this to make you think that what we're doing is beyond difficult, because it's not. But it does require some knowledge of what you've learned in Algebra 2 and Pre-Cal. Exactly. And I'll quickly remind you about the relationships you need to carry over, okay, to make sense of this. And then it also is kind of a frustrating formula because it's kind of really wordy and a lot of stuff going on, which is going to bother some of you. And I'm going to try to simplify that down to a point which will make it more palatable. But historically, people on this test tend to do okay on this. People on the AP test, or when it rolls around to April and May and we're reviewing all this stuff, are like, what the heck? So understand a couple things. One, I'm not even remotely suggesting that you just go, whatever. Got plenty of points to miss. This will be 2 of them. But it's probably a couple points on your AP test, which again, in my opinion, are really easy to come by. Because there's a handful of ways I can ask you questions about this. And a lot of times there's a million ways I can ask you questions about the topic. In this one, maybe 2 or 3. And we're going to go through a lot of those. They all, to me, kind of feel the same. But basically what we're doing today, all right, I'm just kind of warning you ahead of time, it's going to be very complex, the explanation of what I'm doing. The application of what I'm doing is not that complex. Right? I don't want you to just memorize cred, because like most people, you memorize and you just forget it. And if you understand it, it will kind of bail you out a little bit. So kind of earmark this thing. We're only going to talk about this one day. And then when your test rolls around next week or whenever it happens to be, you got to remember to go back and look at it, because I will ask a number of questions on your test concerning this. Okay? But what we're going to be doing here is taking a derivative of an inverse function. Now you might remember from Algebra 2 and Pre-Cal how to find an inverse function. All right? And anybody remember, how do I find an inverse function from a given function? Replace the x with the y and the y with the x, and then what? Resolve for the new y. Well, here's where AP kind of screws you over. When you switch the x's and the y's, they're going to give you equations that you can't resolve for y. And you're like, well, what do I do then? Well, taking a derivative of a function, now you have some other options available to you. One is, and this is probably not ideal, but remember when I switch x's and y's, to take a derivative, I don't have to solve for y, right? We now know that we can take a derivative of an equation that is an implicit equation, right? It doesn't have to be an explicit form, which is like function form. So that's one option. Not the easiest one, but it is one. The easiest option is to understand what's really happening when you're dealing with an inverse. Understand what's really going on. And this is what I'm going to boil it down to. Let's just say we had a function f, all right? And it might be in all here, but let's just say. And I were to plug a value like a into it. This is a regular old function, right? When I plug a number like a in, what does it spit out? Often a different number, right? Because you're squaring and cubing and square rooting or whatever the function's doing. So you get a different value. Well, what does that mean about an inverse if I'm always switching x's and y's for every single value? For an inverse function then, what should happen is, if I plug a b into the inverse function, what should it give me back? The a. And that information right there is critical to understanding what we're doing. Okay? So if you've got that, I think you're halfway there. All right, now I want to show you an example pictorially, and then I want to walk you through this little proof here. Not that you have to know the proof, and honestly, I probably forget it every year too. But I want to show you a picture of a function, a random function, and its inverse. So this, in blue here, in my blue, I know you're black and white blue, but right here, this blue, we're going to call that the function. Oh, by the way, if I plugged b into the function and it gave me a, then when I plug a into the inverse, it should give me b. So you realize, whatever, it doesn't matter which, it just switches the coordinates. Now, here this blue function is f, and then this kind of flatter blue function would be the inverse. How do I know that? Because I also taught, and you probably learned, that inverse functions have a symmetric relationship over the what? Y equals x line. It's actually not the ordinate, it's actually this dotted line, y equals x. And it's basically saying y equals x, so the y of one is the x of the other, which is kind of true, right? The y of one is the x of the other. So they have this reciprocal relationship. Well, if that's true, think about points on the graph. This point, I'm going to call it over b up a. So this point BA is on the f function. Well, if BA is on the f, what is going to show up on the inverse?
AB.
AB, and that AB point right there is on the inverse. Now, track with me here. Think about the slopes there. The slope of this one I actually found, and it actually was equal to 2. Okay, so the slope at that point on this particular function was 2. Well, guess what the slope is here? 1/2. So what I now know is that a slope on an original function, or a derivative on an original function at BA, is the reciprocal of the derivative on an inverse function at AB. Are y'all making this connection? Now, this connection is imperative to understanding how to take the derivative of an inverse function. Because as you're going to see, often on these cases that you're going to be dealing with, I won't be able to find the inverse function. So I got to figure a workaround. Are you with me? Now, if I give you a function and you switch the x's to y's and you can resolve for y, awesome, right? You get a new function, you call it the inverse, and you just take the derivative. Do whatever it takes. You know the derivative rules. The problem is when I can't resolve for y, what do I do to avoid a big mess? So I want you to go back through here, and I want to walk you through this process. So we know from a definition of a derivative, and I say we loosely because you might go, yeah, we. You might not know this, but the pure definition of an inverse says this, that if f and g are inverses, like say g was the inverse of f, it says f of g of x is equal to g of f of x is equal to x. So basically, if I took the two functions and did a composite function with them, right, then I would get whatever it is that I got out. It's kind of like saying, hey, if I plug b into the f and then I get an a, and then if I plug a into the g, I'll get back to where I started. That's what this is saying. Plug plug x into the g and I get a number. Plug that number into the f and I get back to where I started. So that's a definition of an inverse function. And that's why they're starting here. They're saying, hey, if two functions are inverses of each other, then the composite function of them will start with x and end with x. And I could switch the order if I wanted to as well, but we're just doing it this way. Now, if this is a true statement.
Did you cancel out the f and the f?
No, I can't, sadly. Right? Because you know how to do inverses, right? When I do an f of g of something, I can't just, I mean, mathematically, it kind of seems like that happens, but that's not going to help me here, right? All right, so in this proof, I'm going to start out with the definition of an inverse. That's what the definition of an inverse is saying. And I'm going to take the derivative of both sides. Now let's do the math on this. Using what we know about the chain rule, what's the derivative of f of blah of x? How do I start the left side? What do I do when I take a derivative of a composite function? I start with f prime of blah, right? So there's the f prime of blah, and that takes care of the f, and then what do? The derivative of that, which is, this is how I write it, I do inverse f of that. That takes care of that. And then finally, I take the derivative of x, which is 1, and I don't have to bother writing. You see the chain rule?
Yes.
It's a little uglier without a g in there, but like if there was a g in there, you see how that works? F prime of g of x, and then g prime of x, and then derivative of x is 1. So it's the same thing, and again, you're not going to have to know this proof. I just want to convince you that it's true. And then, of course, the derivative of x is 1 here. Now, my goal is what?
To find the derivative.
The derivative of the inverse. So if my goal is to get this by itself, then I should divide by this part.
Right.
So if I divide both sides by that part, I get this, right? Because that part would cancel. And that is technically your formula. But here's the problem. This says the derivative of the inverse function at any particular x value, right, is equal to 1 over what? The derivative of the regular function at that value, whatever that gives me. But the problem is, what happens when you can't find the inverse function?
You give up.
You don't. But it's tempting, right? You want to just grab your ankles, assume the position, and take a beating. But if we can't find the inverse, this is the part that gives us issues. Are you with me? But here's how we bail ourselves out. We bail ourselves out because even if I can't find the inverse function so that I can plug in x into it, I know that the inverse function of a, which is maybe what I'm looking for, is the same thing as what?
Oh, the regular function of b.
The regular function at b. Are you seeing this? Yes, no?
Maybe so.
Okay, right here. The inverse function at an x is going to be we're going to replace it like this. We're going to replace it. Where did I write this? Oh, sorry, no, sorry, my bad. The inverse function of x right here, we're not going to replace that with the regular function of b. We're going to inverse function of x, we're going to replace with what?
b.
B, sorry. So I'm going to replace that whole thing with the b. Are you with me on this?
Yeah.
So the problem I have is I've got to figure out what coordinate. I'm going to probably be given the a, but I've got to figure out what b value would have given me that a. This is the part that I am not going to know. But I'm going to show you a real easy way, and it seems like you go, why would AP do this to me? It seems real, kind of a little hokey. And I'll agree with you there, but they do. Okay? And sometimes they give you tables to do these problems, so the b's and the a's are connected. But the idea is, if I can't find that, then I find the value that would equal that. And from your observation, that value equals that is going to be linked with a through a regular function equation. And that's the key to doing these problems when you can't find the function, is to not use this, but to use the value you weren't given. Notice, I'm trying to find it at a, but I'm going to use the value that goes with, right? What goes with that a? The b value. And I'm going to replace all of that inside part with b. And then, what does it look like I'm doing now? What does it look like I'm doing? Taking the derivative of the original function. So I don't need the inverse anymore. Are you seeing that? So it takes away the need to have the inverse to take the derivative of it. I'm going to take the derivative of the regular function, but not an a. I'm going to take it of the coordinate that goes with that a, plug that in, and then why do I flip it? Why do I put it on the bottom? Because it's a reciprocal, right? Because the function of the inverse is the reciprocal of the original function. Sorry, the derivative, the slope of the inverse is the reciprocal of the original slope. So the slope of the inverse is the reciprocal of the original slope. The only difference is, instead of finding the slope of the inverse at a, right, we're going to find the slope of the original function at b, and then flip it from here to here. Are you piecing that together a little bit? Yeah. Now, if you can find the derivative if you can find the inverse, well then you can use this formula, right? If you can find the inverse function, you just go, oh, like if I wanted to find this, I find the inverse right there, I plug a 3 in the inverse, I get that new value, I take the derivative of the function, plug in that value, and I flip it, put it under 1, and I'm home free. But when you can't find the inverse function, this allows you to not need the inverse function. This allows you, but you do have to do a little work to find that b. So let me just show you an example. Okay, now watch this process. So here's my original function. All right, this is on the back page, and you don't have to take notes on this one, obviously, because I want you to have something written down. And I'll walk you through it. I know it's a lot of words. You're not going to have to do this much, right? You're just going to know the ideas, but I'm explaining it all. So right here, I want to find the derivative of the inverse of f at x when x is 3. So essentially, I'm saying the derivative of the inverse at 3. That's what I want. So my first thought was naturally, oh, I guess I got to find the inverse function. So I changed y to x. Where did I do that? I changed y to, here's my original function, so I changed y to x, and I changed x's to y's.
Plugged in the point.
Why did I write it like this? Dadgummit. Okay, should have made better notes. Hold on.
It's okay.
Check this out. I'm going to change y to x and x to y. Now, what's wrong with this right now when it comes to finding the inverse? You're stuck, aren't you? Are you with me? But is this the inverse function? Yeah, it's just not pretty, right? It's not solved for y, but it is the inverse. And right here, this says that I should be plugging 3 into the derivative of this. I'm sorry, according to this function, this says I should be plugging 3 into that inverse, right? But I'm plugging 3 into the inverse function for what? For the, that's an x value on the inverse, not the original. So I'm going to come in here and plug a 3 right in here. But I run into one small problem. How on earth do I solve for that? Well, believe it or not, AP, so ignore this or just switch these to x's and y's. Sorry about that. Right? So, when you do this, you have to solve for y by literally guessing and checking. Here's the upside. I have never seen this guess and check go beyond -3 or 3 and their whole numbers. So it's not like you're going to have to go, does 7/8 work? Does -1 million work? So I just start checking. All right, does 0 work in here? No. Does 1 work in here? No. Does 2 work in here? Yeah. 2 cubed is 8, a fourth of 8 is 2. 2 plus 2 is 4, 4 minus 1 is 3. Boom. Now if I tried 2 and it didn't work and 3 and it didn't work, I'd go back and try -1, -2, -3. I've never seen it beyond that. And usually it's plus or minus 1, plus or minus 2, or 0. Okay? So what that means is, if 2 works, this is where it becomes important. 2 is the what? 2 is the y value of the inverse. So think about that. The y value of the inverse is the same thing as the what? X value of the original. And what was our alternate equation? I'm sorry. What equation would I use to figure out what goes with 2 now? That. So if I plug a 2 in here, what do I get in the original function? A 3. We just confirmed that. Are you with me? So what this is saying is 3 in there for x in the inverse gave me a 2. Well, a 2 in there for f would give me a 3. And now that I've established that, even though I don't have my inverse function directly, what could we use as an alternative?
2.
And what do we say we could use? Instead of using this definition, we said instead of using f -1 of 3, we could use what?
2.
The 2 in its place. So instead of finding this value, I kind of found it, I just did it a little bit differently, right? I'm going to replace that with a 2, and then all I have to do now is to take the derivative of the original function at 2 and put it in the denominator, which would be flipping. So what's the original function?
3 times 1/4 x squared.
The original function is what? 1/4 x cubed plus x minus 1?
Yeah.
So the derivative of the original function is
3/4 x squared
plus 1, and the derivative of that at
2
2 is just 4. So all of that becomes a 4 on the bottom, and I flip it to a 1/4. Are you seeing that? Now again, if I could find the inverse function, if when I switch those x's and y's like up here, which should have been y's right here, once I do that, if I could solve for y, great. And sometimes you can, but it's rare that you can. So when you can't, say, all right, I'm still going to switch the x and y's. I'm still going to plug 3 in for the x of the inverse, but I'm going to find the y value that would make that true. And what that does is, it allows me to bypass this because technically I did it, right? I'm plugging in 3 in the inverse function in order to find its value. Well, you found it. By plugging that in there now, I no longer actually have to know the inverse function to take a derivative of it. But I could skip through all of this if I could actually find the inverse function. Because if I could find the inverse function, like if I could actually do this, then all I have to do is take the derivative of that at 3. But it is rare that you actually can. Are you seeing that? Okay, so let's take a look at a few more of these. You can see probably why I'm suggesting that this is not as straightforward. It's a little hard to remember. So let's look at this one. Here's a function. Find the derivative of its inverse at -3. So my thought was, oh, find the inverse. Crap, I can't solve for the inverse. But I do know that that is the inverse function, right? So I'm going to go, all right, well, I can plug a -3 in there, right? So if I did plug a -3 in there, I can technically solve for that y value. But I'm going to have to guess and check. What'd you get? Okay, so if I plug a -1 in there, I get -1 minus 4 is -5, plus 2 is -3. That's true. So y is -1. So that tells me that in the inverse function, should I have plugged a -3 in there, I get a -1. Well, I am going to replace that in my definition. And my definition says the derivative of the inverse of x is the same thing as 1 over the derivative of the function, not at x, but at the number that goes with that x. So not at -3, but at the function that goes with that -3, which is -1. So all I have to do is take the derivative of f, which is what? 3x squared plus 4, and plug the -1 in, and then flip it. 1/7. What about, see, these are all old AP questions that might have changed, I might have changed the numbers. And I'm going to pick just a couple of them. How about, these all kind of look the same. So which one? 1, 2, or 3 you want to do?
2, 1.
You all see that they are essentially the same question? You what? You like 3?
Yeah.
Okay, look at 1. Look at 1 and 2 real quickly over here on the right. Notice it says derivative of the inverse of g, derivative of the inverse of f. That's the same thing though, right? The ddx of the inverse of f. Just a different way to write it. Okay? So right here, this is saying the derivative of the inverse of f at 2. So I want the derivative of the inverse, so first I'm going to try to find the inverse. X, y to the 5th plus y. Crap, I can't find the inverse. But at an x equals 2, at 2 on the inverse, in for x, that allows me to find the y coordinate, right? And this is the inverse, right? And what's going to be y in this case? 1. So therefore y equals 1. Well, that tells me that f inverse of 2 equals 1. Well, that would mean f of 1 would be 2. And now I can say, well, our definition says the derivative of the inverse at 2 is the same thing as what? The derivative of the regular function, not at 2, but at 1. So I plug a 1 in there, and how do I take a derivative of a regular function? 5x to the 4th plus 1, flip it and plug a 1 in. And remember, when you flip it, it's not a negative reciprocal like you do with perpendiculars, right? They're just reciprocals. Now, that kind of seems pretty much like the ones we've been doing. I'm trying to find something that looks a little different. Okay, look at number 5. Okay, now, they give you a bunch of junk now, so you don't even know the function. But they give you some information, and this one's kind, because most of the time they bombard you with extra information. But let's think about it. The derivative of the inverse at 5. Well, according to my definition, the derivative of the inverse at an x is the same thing as what? Of the regular function at the inverse of that x. So let's look up here. Do I know anything about the inverse of x? That's my hardcore definition, right? So this is my thinking. All right, I know that if f of 4 is 5, what do I also know? F inverse of 5 is 4. So if this was f inverse of 5, which it sounds like they want me to do, right? 5 there, 5 there. This is what they're wanting me to do. Well, since that's true, I know that f inverse of 5 is 4. I can replace that with a 4. And I'm already given f prime of 4 is 2/3. And 1 over 2/3 is 3/2. So, but I got to know my definition, don't I? Now, you might not have to know the definition if you didn't do all this and you're like, I don't remember any of that. All I remember is if this is the derivative of the inverse, I'm going to take the derivative of the original function at the number that goes with 5. Now, you remember, what you got to think is this. 5 is what I would have plugged in the inverse. So on the regular function, I have to figure out what would have the y value have been. So you got to look up and look for that. Sometimes they have lots of points up here to choose from. So you got to go, oh, well, this meets that's narrative. So I guess it's the 4 that I'm going to be using here. And then you go find that from the chart or the table or the information you're given. All right, this one gives you a little more information to confuse you. Check out 6. G, derivative of G at 3, derivative of G at 7, and the derivative of the inverse of G at 3. Now, we got a couple options. I know the derivative of the inverse at 3 is 1 over the derivative of the function at the inverse of 3. That's the flat out definition. Do I have the, not F. Do I have G inverse at 3?
Yeah.
Do I? Not directly, right? But I know that the inverse at 3 is equal to something is the same thing as G of that something equal to 3. Do I have that?
Yeah.
Right here. So that must have been a 7, right? So I can replace the inverse of G with the 7. And I have G prime of 7. But what do a lot of people just pick? They get this messed up and they go, oh, just pick G prime of 3 because I'm doing the 3. But if I use that shortened definition, which is this one, I don't just say the derivative of G at 3. I don't say that. I say the number that goes with that 3. And that's why I have to identify what that is. And what is g prime of 7? 3/4, and 1 over 3/4 is 4/3. Yep.
Do we have to show like all that work or?
On a multiple choice, you have to show anything.
Okay, like even on your test?
On my test, I show everything.
Okay.
Like,
'Cause,
yes.
like, you can just look and just see that it's the reciprocal of the g prime of 7.
I can,
I have no
and you
idea.
can't, you might be able to too, but if you don't show me any work and you're wrong, like, I'll be honest with you, if you, something like this, if you pick the right one, I'm okay with it. But if you don't, and you showed good work and accidentally got to here and wrote circled 3/4 or whatever, and I could see that there was something, you might get some of those points. But this would probably be a 3-point question on the test. And if you were wrong here, but actually had something good and made a careless error, you might get 1 of those 3 or 2 of those 3, it's possible. But yes, on a problem like that, that I don't think requires any work and it's multiple choice, it might be minimal. But I'm gonna show it just in case. Okay, we've already done something like this.
Number 9.
Okay, tables. Man, you'll get better at these if you struggle on this one, but let me just tell you that AP loves a table. Like, I mean, really loves a table. So let's take a look at that. Why do you think they say this? Why do they say h of x equals the inverse of f and then the derivative of h?
Because this is in the table.
No, it's discrete. Okay? They're doing that to kind of mess with your brain. Because they could have easily just said the derivative of the inverse at 3. Couldn't they? So they're trying to make it wordy. Don't assume the position. Don't get thwarted by their little evil ways, right? If h is the inverse, the derivative of the inverse at 3. Right? So essentially, if you don't like the way that looks, then think like this. Because there's no h's in here, are there? So if you need to make that translation, think like this. That's what this is saying. The derivative of h, which is that. So what do I do on a situation like this? To find the derivative of the inverse at 3, I've got to go 1 over the derivative of the actual function where the inverse of 3 exists. Now, because I don't know anything about the inverse from this, do I? Not anything. All I got is derivatives. Don't confuse derivatives with inverses. So what I have to do is try to figure that out. So I think, well, if the inverse at 3 is blank, then f of blank would have given me what? 3. So what number would I plug into f that would have given me a 3? Can y'all see that in this chart? Can you see that I would have plugged 2 into f to give me 3? So that means 2 would be what I'm going to replace that with. Are you seeing that? So I replace that with a 2, and the derivative of the function at 2 is on this table. So the derivative of f at x equals 2 is now 1. So I plug a 1 in, and don't forget to flip it. And when I say flip it, I mean, when you plug a 1 in, it already is flipped if you're using your formula. If you're not using your formula and you're just finding the derivative of that, whatever you get, just remember that it is in the denominator, which means it does need to be flipped. Don't go and flip it twice. You know. One more time, what about this? So it says find the derivative of h at 1, but h is the inverse. So what am I finding? The derivative of the inverse at 1. Well, my formula says 1 over the derivative of the function of the inverse at 1's value. I don't have anything about the inverse of 1. All I have is stuff about f, g, and their derivatives. So again, the inverse of f at 1 is equal to something, and that means f of something is equal to 1. What something spits out a 1? 0. So that means that f inverse at 1 is a 0. So I can replace that with a 0, and I can definitely plug 0 into the derivative function, and it gives me a -1, and 1 divided by -1 is a negative. Yep. Sure. What about number 12? Now, talk to me. Can't I find the inverse of that?
Yeah, you can.
X equals root y minus 4, square both sides, add a 4. Okay, got my inverse. So, it says find the, if this is h inverse now, what's the derivative of h at 2? What's the derivative of h inverse at 2? Well, I can actually take the derivative of this. 2x. Done. I didn't even need my rule because I could find the inverse, right? But assuming I couldn't find the inverse, if I couldn't, I could still say, well, I can still switch the x's and y's, right? And if I switch the x and y's, I'm saying basically a 2 in for x in the inverse, eyeballing that. Okay, actually, you don't have to eyeball it. You could actually solve it. But you end up getting y equals what? And you square both sides and add a 4. 8. So this is saying the derivative of the inverse at 2 is the same thing as the derivative of the function at where the inverse of 2 exists, which is now what? 8. So what's the derivative of the function at 8? Well, you could go back to the original function, right? What is its derivative? Double that on the bottom, derivative of the inside part on the top, plug an 8 in, and what do you get? 1/4. So I put 1 over 1/4, and what does that give me? Which I would have found a whole lot easier if I actually found the inverse like I did in the original way, right? But most of the time you can't find that inverse. This was one that you could. But what about this? Oh man, there's a sine curve. No. Not me, man. I like it. Okay, so if this is my function and I'm looking for the derivative and it says g is the inverse of f, why do they do that to mess with you? I don't know, but basically what they're saying is g is the same as inverse of f. So I'm taking the inverse, or the derivative of the inverse of f, basically. Can I find the inverse of that? Make that an x and resolve. How do I solve? Inverse sine. Y'all with me on that? Inverse sine both sides? Man, if only I knew the derivative of inverse sine. Oh goodness, we learned that yesterday. Right? And if you know that formula, this becomes the easiest problem on the test. Because right now, if that's the inverse right here, this is the inverse function, right? This is inverse of x. So to take the derivative of the inverse, what do? Square root of 1 minus the u squared over the derivative of the u, which is 1. And all I have to do is the inverse of f's derivative at a half is plug in a 1/2 in there and simplify it. So what's 1/2 squared? What's 1 minus 1/4? So I get 1 over the square root of 3/4. Now, sadly, that's not an option, but does that simplify? 1 over the square root of 3 over 2. And what does that become? 2 over root 3. And a lot of times they don't rationalize, and they didn't hear. So that's fine. If you didn't see that, then rationalize. You can get 2 root 3 over 3. Look for that. Are y'all seeing this?
Yes.
But I knew the inverse. Now, what if you forgot the inverse function? Which most people do in May 5th. Because it's so long and we cover it one day and they move on. Well, if that happens, don't forget you have another option. So, if you don't remember any of this, you're basically saying this. Okay, that's technically the inverse, and I'm plugging 1/2 into that. Where does sine equal 1/2? And remember,
30 degrees.
but I can't keep, so pi over 6. So at pi over 6, that's true. Or you can even think better, inverse sine of 1/2 would be 30. Now remember, sorry, it's pi over 6. Now remember, because we're dealing with an inverse sine is defined, and tangent, those are the only two you'll deal with on the test, are defined where? Between negative pi halves and positive pi halves. So you never can get like a 150 or anything like that over there in the second and third. Those are definitions of inverses. So remember, you got to pick your angle. Like if it was a negative 1/2, I'm not going to say 330 degrees or 11 pi over 6. I can't do that because this is an inverse we're essentially dealing with right here, right? Inverse. So I would have to use negative pi over 6. But in this case, positive pi over 6. So what that means is, if I needed to do this, which is what it's asking me to do, I could cheat and do what? The derivative of the regular function, but not at 1/2 at pi over 6. Now what is the derivative of the regular function? Cosine. So I'm going to do the cosine at pi over 6. And what's cosine at pi over 6? Square root of 3 over 2, and we're back to where we were. Two options. But man, wouldn't it easier just knowing that inverse trig definition? Well, if you don't know it, certainly have the other one in place. But I can tell you this, 5 months from now, or 4 months from now, it's going to be hard to remember this formula when we haven't touched it. But if you do know this process, you're probably not going to have forgotten that the derivative of sine is cosine. So you certainly can bail yourself out. But it is, to me, worth reviewing that inverse definition, because when it comes to using it, it's not difficult if you just know it. All right? What else?
There we go.
We're still baking. Tell you what, we got a little bit of time. 5 minutes. On the miscellaneous day 3 implicit stuff. Let's just plug away. This is an old 1998.
So you just do proof here?
Pardon?
You just do proof here?
Yeah. So on A, here's why they did this on A. It says show that that's true. And you're like, really? I just got to show my work and it's giving me a backup, it's giving me an answer to proof it against? Yes. And the reason why is they don't want you to have the wrong one because they want you to be able to answer B and C. But they're going to look at your work. And your work's not going to magically give you this straight up. It's going to be something that would simplify into this. So we need to show that this would have been true. So how would you have taken the derivative of that expression to end up with this? What would you have done first?
6y squared dx
6y squared dy dx plus, what are you going to do for this?
plus
Product rule.
yeah,
So here we go. For the product rule,
first
all right, so we've got first d second, which is dy dx, plus second d first, which is 12x, minus 24x, plus 6 dy dx equals 0. And you can see real quickly that I have 3 dy dx terms, which makes sense to me when I look at my final answer, because I'm going to be factoring the dy dx out of that, and it should have 3 terms that I divide over to the other side. That part makes sense. And I need to subtract this 12xy and add that 24x to the other side. So when I do that, I get 24x minus 12xy. That makes sense because there's 2 terms on the other side, and even though the numbers aren't the same, my guess is there was some simplifying that went on. And then what happens when I factor out the dy dx? I'm left with 6y squared plus 6x squared plus 6. And when I divide both sides by that trinomial, I get that. And then I still need to show how I got this, so what would you have done in this case?
factor out 6.
Factor a 6 out of the top and the bottom and cancel it. It's the same thing as dividing the top and the bottom by 1/6. And if I divide that by 1/6, it's a 4, that it's a 2, that it's a 1, that it's a 1, that it's a 1. So I have just shown that this was true. And my guess is you would have gotten a point or 2 points, maybe 2 points for the derivative, probably 1 for doing all the non-implicit stuff, and then 1 point for the explicit stuff, and then a point for this last bit of process. But that's probably worth 2 to 3 points in 1998. And then here's the upside of this. By doing this, now it's not going to snowball any. But again, I haven't seen a 9-point problem in years, but this would have been in the process. So now it goes right in the equation of each horizontal tangent line. What do you know about horizontal tangents? What about their slopes? The slopes are 0. So I would say something quick like, hey, the slopes would be 0, therefore, although probably that's not necessary, I've never been a grader, never will be a grader. Sounds like literally, like that's the one thing I hate about teaching, is grading papers. Why somebody would go and give up 2 weeks of their summer to grade? I got enough. It just sounds excruciating for me to grade from 8 in the morning till 5 at night, all day long, the same question for 2 weeks.
You probably have to become a better teacher of the test.
I don't know.
I would argue that's probably true if you were early in your years, but they only ask people, like the people I've talked to, always say that. I'm like, that's why you go back, and they're like, not really, because I grade the same problem over and over again. And the people that I know that enjoy it are like, I've made such good friends, and I'm like, that's sweet and all, I got good friends, and you know, what?
I already got friends.
Yeah.
Don't gotta-
So if you're a people person who just likes that, then whatever. So we got 1 more minute, but bottom line, what would I do? Now careful, look at this. I can factor out a 2x, and I'm left with 2 minus y. So what does that mean? At 0, x equals 0 and y equals 2. So those are my coordinates of not together. They don't work together. But you would have to go and find what? Those points. Now wait a second. Horizontal, what does that mean? It crosses the y-axis. So this one, I've already got the equation. But this one, I would have to find the y-coordinate to find out a horizontal tangent line. All right, y'all have a great weekend.
Wait for me.
All right, man.